sorry, the threshold voltage of the device of the NMOS device will rise. Okay, in this case, if VSB is not equal to 0. Okay. Uh, and we know that the equation for ID in linear, and this is the equation for drain current in saturation region. Okay, the linear current is given by mu n C oxide by 2. Okay, W by L. This parameter will remain same in both of the cases. Uh, uh, into 2 into VGS minus VT as a function of VSB. Okay, into VDS minus VDS square. Okay, we'll join. So this is the equation for ID in linear mode of operation. Okay, and remember where is this VT, the threshold voltage is coming? This is coming here. Okay, so if VT rises to a more value, to a greater value, what happens? This term becomes lesser. If this term becomes lesser, then the overall effect on the current would be such that the current would decrease. Okay, the current will decrease. Now look at here, the saturation current is given by this equation. Okay, this parameter is same into VGS minus VT whole square into 1 plus lambda VDS. Now this 1 plus lambda VDS is coming from that channel length modulation effect. Okay, and again this is VGS minus VT whole square here. Okay, so again if VT becomes a higher value in the case of NMOS, okay, this term will become lesser. Okay, this term will decrease, this whole value will decrease, and we would expect that the current starts to decrease. Okay, so the effect of a voltage applied here, okay, is such that the current values are decreasing actually. So the linear current and the saturation current both are decreasing. Okay. Okay, so here the terminal voltages and currents of the NMOS and PMOS transistor. Okay, we have already seen the symbol, but still, let us see with the with all the terminal voltages that are applied here. So for the case of N-channel MOSFET, NMOS, okay. So we know that the MOSFET is having four terminals. The source, this is the source, okay, and this is the gate, and this is the drain, and this is the body. Okay, B for body or bulk, right? And the symbol you are aware of, how does the symbol is drawn for N-channel MOSFET. Okay, right. Now this is gate, this is source, so the potential difference between gate and source is VGS. Okay, VGS. Okay, right. The potential difference between source and body is VSB. VSB, this is VSB. Okay, and note down the polarity, because since we are writing VSB, so it will be calculated with respect to source. It will be VS minus VB. Okay, so you know this thing that VSB will be equal to actually VS minus VB. Okay, and hence the polarity is taken positive for source and negative for body for calculating VSB. Okay, and this is VDS, and this is the potential difference between drain and source. So drain positive, okay, positive here, and for source it will be a negative, and this is the potential between the drain and the source terminal, like this. Okay, so these are the voltages that are actually affecting the value of current that flows through the MOSFET. And similarly, we will have the P channel MOSFET. The arrow will come out in this case instead. And again, we are having the four terminals: the gate, the source, the body, and the drain. Okay, so we will have gate and source VGS. Okay, we will have again VSB, and then we will have VDS between drain and source, between drain and source VDS. Okay. Now, one point regarding this, that in the channel, in N channel MOSFET, generally we ground the source terminal, and the drain terminal is connected to a higher potential. Okay, and this is reversed in the case of P channel MOSFET, that the drain terminal will be connected to the ground or the lower potential, and the source terminal will be connected to a higher potential as compared to drain in the case of P channel MOSFET. Okay, so this should be clear. Okay, and most of the time we will be dealing with N channel MOSFET. Okay, and but many a times you will see P channel MOSFET also. So, and the two things are complementary to each other. So if you understand one thing, the other thing you will understand naturally. Okay, so this substrate bias effect can significantly change the threshold voltage value. Okay, and hence the current capability of the MOSFET. Okay, so this is the equation. So till now, whatever effects, whatever equation that we have derived, okay, for the drain current, for linear and saturation region, including those two effects. The first effect was the channel length modulation, and the second effect was this just we have seen substrate bias effect. Okay, so including those things, we can write, okay, for N channel MOSFET. Okay, uh, the current could be zero, and the current will be zero means the device is off, and this will happen only for this condition, that is when VGS is smaller than threshold voltage. When the gate voltage is smaller than its threshold voltage, we will assume that the device is off. So remember this condition. This says that the device is in off condition. It is not conducting. Okay, we will assume like this, and this is for off state. Okay, and these two currents are when the diode is conducting. Okay, and we know that when diode is conducting, we have two different regions of operation. The first is linear region or triode region, and the second is the saturation region. Okay, and we have got different equations for the linear current and the saturation current. Okay, and the equations are like this. For linear current, this is given by, this parameter will remain same. Okay, so mu n C oxide by 2 into W by L. Okay, where mu n is the mobility of free electrons, C oxide is the oxide capacitance, W is the width of the channel, L is the length of the channel. Okay, and within brackets we have 2 into VGS minus VT into VDS minus VDS square. Okay, and the condition for the MOSFET to be operating in linear mode, okay, this is important. You should be able to recognize the difference between linear and saturation region. Okay, obviously this is the condition, this is the first condition, that when VGS becomes higher than VT, then we say that the device is conducting. This condition should be met for both states. Okay, here also for the saturation state, that when gate voltage is higher than its threshold voltage, the device is on and the current will flow. Okay, now the current would be a linear current or a saturation current. Okay, and for the linear case, this is the condition that is to be satisfied, that is VDS, that is the drain voltage, should be smaller than VGS minus VT. VGS minus VT. Okay, and remember this VGS minus VT is actually V Anyone remember what is this? VD sat.
Sir, B.
Yeah, yeah, right. This is VD sat. Okay. This is the value of VD sat, the voltage at which the device starts to saturate. Okay. So when the voltage applied at the drain terminal is less than the VD sat, then we say that this is in linear region. Okay. And when voltage applied at drain terminal is higher than VD sat, then we say that it has entered into saturation region, and the current equation for saturation is given by this equation. Okay. So this parameter will remain same, mu n C oxide by 2 W by L. Okay. And here we are having VGS minus VT whole square, and this is the effect of channel length modulation. Okay. So many a times in the question, uh, you may take this effect into your calculation, or you may ignore this also. So this will depend on the question that is being asked. Okay. But still, for the sake of showing here, it has shown that the effect of channel length modulation here. Okay. And the overall equation for ID set becomes like this. Okay, so this is the equation for n channel MOSFET, the current equations. Okay, who is coming? And this is the equation for p channel MOSFET. Okay, and if you have understood the n channel MOSFET equation, then you can just do the reverse thing in terms of the polarity of the voltages applied, and you will get the equations or the values for the respective p channel MOSFET. Okay. So in this case, this is ID is 0, that device is off when VGS is higher than VT. It is just the reverse of the N MOSFET. So in N MOSFET, we had this condition that when the gate voltage is smaller than threshold voltage, then the device is off. But here, when the gate voltage is higher than threshold voltage, then we say that the device is off. Okay. And these inequality conditions will get reversed. Okay. For linear and for saturation. Okay, only there will be a change in the, or there will be a reversal in these inequality conditions here. Okay, and the equations will remain same. The equations are same. This is mu n C oxide by 2 W by L into 2 VGS minus VT into VDS minus VDS square for linear current, and this is for saturation current, that is mu n C oxide by 2 times W by L in brackets VGS minus VT whole square, again in brackets 1 plus lambda times VDS. Okay, so these are the equations are identical, and the condition is just reverse. Okay, and the voltage conditions, the voltage polarity may get reversed with respect to n channel MOSFET. Okay, with respect to n channel MOSFET. So these are the final equations for n channel MOSFET and p channel MOSFET. The equation for the drain current that will flow through the device. Okay. Now let us go through some small examples, like because this is important that we should be able to decide that in which mode the transistor is operating. Okay, we should know. So let us see that we have a transistor. This is N MOSFET. Okay. So which mode is the transistor operating in? Which mode? Cutoff, linear, or saturation? Okay, this is the gate voltage. So let me write here. This is gate voltage 2 volts. Okay, this is the drain terminal. So this is VD. Okay, and this is the source terminal. This is VS. Okay, and the threshold voltage for this NMOS is given as 1 volts. So can you decide? Okay, which mode this is operating in? So first of all, we should check whether this device is on or off. Okay, And for deciding the device is either on or off, we should check for this condition. VGS is smaller than VT or not. So here, what is VGS? VGS is VG minus VS, that is
Sir,
2.
1.5 volt.
Yeah, 2 minus 1.5, 2 minus 0.5, that is equal to 1
1.5 volt.
1.5 volt. And this 1 point, okay, 5 volt. Okay. And VT, the threshold voltage is 1 voltage. So VGS become greater than VT, threshold voltage. So what can we conclude? What can we conclude that this device is on or off? Hmm?
Sir, on.
This device is
Sir,
on. Yeah, right. Because this condition is satisfied. So one, the first thing is established that this device is on, right? Now, if this is on, this can be either in linear region or in saturation region, right? So the second thing is to see whether this device is operating in linear region or saturation region. Yeah, tell me. So for deciding
in
whether the
linear region.
linear region, why in
Yes,
linear
sir.
region? Why
Sir,
linear?
VDS is equal to 0.2 volt. Sir,
VDS is equal to just a minute. VDS is equal to 0.2. Why?
2 volt.
V,
Sir,
v,
VD minus VS.
okay, VD minus VS is 0.7 minus 0.5, 0.2 volt. Okay. And what is
Yes,
VD?
sir.
VD sat? What is VD sat?
VG,
VD
VGS
sat.
minus
Yeah,
VGS minus VT.
yeah, right. VGS minus
VT
VT. Okay. And VGS we have calculated here 1.5.
1.5 volt.
1.5 minus
5
1
minus 1.
becomes how much?
0.5.
0.5 voltage. Okay.
Yes, sir.
Yeah, and
Sir,
VDS,
VD,
right.
VDS
Now,
is less than VDC.
right. Now you compare this VD and VDS. Okay. You compare these two. If VDS is smaller than VDSat, then the device is in linear. If VDS is higher than, greater than VDSat, then the device is in saturation. Okay, so this, since this is smaller than VDSat, so this device is working in linear mode. Okay, okay. So VGS is 1.5, VDS 0.2, VDSat becomes 0.5. So this device is in linear mode. Okay. Look at this, students. Any doubts from any student? Because this funda should be clear. Okay, this should be clear to everyone. You should be able to decide quickly if the voltages are given that the device is working in cutoff, linear, or saturation. This one, VG 2 volts. Now VD is 1.5 and VS is 0.5 and the threshold voltage is 1 volts. VBS is 0. Okay. So first, whether the device is on or off.
The
VGS,
device is on.
device is on.
Yes, sir.
VGA, yeah, let's see. VGS 2 minus 0.5, that is 1.5, and 1.5 is greater than threshold voltage, so the device is on, right? The device is on. Saturation or linear?
Sir, saturation.
Saturation. So okay, VDS is 1.5 minus 0.5, that is 1 voltage. VDS and VDSat is VGS minus VT, that is
That
1.5. Okay, so this is which one? Linear or saturation?
the saturation.
So this is saturation. Okay. Other students, is it clear? Yeah, class, students, everyone. So there are two steps basically in determining the region of operation. First, you decide whether the device is on or off, and after deciding that, if the device is on, then go for the deciding that whether the device is in linear or saturation. Okay. Okay. This case,
Device is off because VGS is less than V threshold.
this is off. Okay.
Yes, sir.
Okay. VGS VG minus VS 0.5. Okay. And VDS 0.5 minus 1.5 minus 1 voltage. Is it off? Hmm?
Sir, V threshold is 1 volt, no?
Yeah, with threshold is 1 voltage.
Sir, VGS is less than VT, then
VD sat is VGS minus VT. Okay, VGS minus VT. VGS minus VT. What is VGS?
VGS is 0.5 volt.
0.5 or 1.5?
Sir, 0.5 VGS.
Okay, now look at this structure. The structure for MOSFET. Okay, this is the simple structure. Okay, gate, oxide, semiconductor, and N plus this is source, and N plus this is drain. Okay, now look at the structure and you will see that the structure is completely symmetrical. The structure is completely symmetrical in nature. So it says that you can use either of these terminal as source or drain. So you can interchange the source and drain terminals with no effect on the device performance. Okay. You can use either this one as source or drain, and similarly you can use this terminal as a drain or source. It will have no impact on the operation of the device. Okay. So keeping in mind this thing, okay, and this symbol is just to symbolize that thing, okay, that we are using this source, but we are free to choose either this as source or drain. Okay, and the more important point is that generally we keep the source at the lower potential. So in this case, this terminal is at lower potential, so we can take this as the source. That Vs is 0.5 voltage. Okay, so this should be treated as source in this case. This source and this as drain. Now you calculate by assuming that this Vs is equal to 0.5 voltage. VGS would be 2 minus 0.5, that is 1.5. So this is wrong. 1.5. Okay, 1.5. And VDS would be 1.5 minus 0.5, that is 1 volts. Now you calculate VD sat, that is VGS minus VT, 1.5 minus 0.5, that is, 1.5 minus 1, that is 0.5. And VDS is higher than VD sat, so this device will be in saturation. So are you getting the things? Whether you connect this 1.5 voltage here or here, or you connect 0.5 voltage here or here, okay, the device will not differentiate. This symbol is for our convenience. Okay, this is not affecting the device performance. The device is okay whether the current flows from source to drain or drain to source. It has no concern about it. Okay, so we will see that which terminal is connected to lower potential, and we will take that terminal as the source terminal. Okay, and the other terminal which is connected to higher potential as the drain terminal. And then you will calculate these parameters and decide whether the device is in linear or saturation. Okay, so keep this thing in mind. This one, What if gate and drain is shorted? This is the drain terminal, this is source, and this is gate. So you have shorted this gate and drain. Shorted means they are connected directly without any resistance. So it means that Vg is equal to Vd in this case. Okay. So Vg becomes equal to Vd, and both are equal to what is the value?
2 volt. 2
Yes,
volt.
2 volt. Now you calculate Vg 2 voltage, Vd 2 voltage, and Vt is 1 voltage given as threshold voltage. Okay, Vs is 0. Vs is 0. So now you decide. VGS becomes 2 minus 0, that is 0 voltage, sorry, 2 voltage, and VDS is again 2 voltage. So this is saturation. So remember this point. So whenever the gate and drain terminal is shorted, the device will always work in saturation mode. This point is important. So if you see the gate and drain connected, shorted, you can decide immediately that the device would be working in saturation mode. Okay. Now, till now we had seen the characteristic of the device. Okay, we have studied something about the device, the MOSFET, the N MOSFET and P MOSFET. We had seen the derivation for its current equations. Okay, now let us see some application. Let us try to build the circuits. Okay, using that device. Okay, the first thing, that is the most fundamental thing, is the inverter. Inverter. Okay, inverter is the most fundamental logic gate. Okay, means the simplest logic gate that performs a Boolean operation on a single input variable. Okay. It has one input signal and one output signal. Okay, and all other gates are having more than one input signal. Only inverter is that gate which is having just one input and one output signal. Okay, so this is the symbol of an inverter. You are very well aware of this. This is the input signal A, and this is the output signal B, and B is the logical equation says that B is equal to A bar. Okay, and this is the truth table for this inverter. This is input, this is output. So A is a single bit, one single signal, so it can assume two values, either 0 or 1. Okay, if it is 0, then B becomes complement of 0, that is 1, and if it is 1, B is simply complement of 1, that is 0, right? So this is the truth table. And this is the voltage transfer characteristic. We say that this is VTC, or the voltage transfer characteristic of the ideal inverter. So the term is voltage transfer. Voltage transfer characteristic means it is a relation between voltage parameters. And if you see this term transfer, so it means that it is relating the parameters between input and outputs. Okay, it is not relating the parameters at one side of the port. It is relating the parameters across the ports. Which parameter? Voltage parameter. So one voltage will be taken from the input side, and the other voltage will be taken from the output side. Okay. So this y-axis is the dependent parameter, that is output voltage, and x-axis is the independent parameter, that is input voltage. So when you plot the graph between input and output voltage for an ideal inverter, okay, we will see that the graph will come like this. Look at this. This is straight, and this is the transition occurring from 1 to 0. Okay, and this is 0, logic 0. So this particular value, when output voltage is equal to VDD, okay, and remember that for this particular case, we assume that the voltages are swinging between 0 and VDD. Okay, so 0 is the lowest level and VDD is the highest level. Okay, now this VDD can be anything. VDD can be 1.5 voltage, 1.8 voltage, 2.5 voltage, 3.3 voltage, or 5 voltage, depending on the technology. Okay. So when input, we say that when input is low from 0 to VDD by 2, the output is high. Okay. And when input is high, that is from VDD by 2 to VDD, the output is low, because this is inverter. This is performing the inverse operation. So when input is low, output is high, and when output is input is high, output is low. Simply, okay. So this is the logic 1 output, and this is logic 0 output. So this is a simple inverse relation between output signal and input signal. So V out is actually this terminal, and V in is actually this terminal. Okay, right? So from here we will resume in the next class. Any doubts you can ask, and you can give your attendance in the chat box.